Time is a fundamental aspect of the universe. It governs our lives from the smallest atom to the largest galaxy. In physics, time is considered a dimension, just like space. Together they form a four-dimensional fabric called spacetime. Imagine a vast, flexible sheet. This sheet represents spacetime. Objects with mass, like stars and planets, create curves in this fabric. These curves are what we experience as gravity. Time, however, is not absolute. It does not flow at a constant rate for everyone. Einstein's theory of relativity revolutionized our understanding of time. It showed that time is relative, meaning it can be experienced differently depending on an object's motion and the strength of the gravitational field it is in. Einstein's theory of relativity, proposed in the early 20th century, shook the foundations of physics. It consists of two theories, special relativity and general relativity. Special relativity deals with objects moving at constant speeds, while general relativity tackles acceleration and gravity. One of the mind-bending consequences of relativity is time dilation. Imagine two identical clocks. One clock remains on Earth, while the other travels into space at incredibly high speed. Upon its return, the clock that journeyed through space will show less time passed compared to the Earthbound clock. This difference in time is due to their relative motion. The faster an object moves through space, the slower time passes for it relative to a stationary observer. This phenomenon has been experimentally confirmed using atomic clocks on high-speed jets and satellites. Time dilation is not just a theoretical concept, it has real-world implications for technologies like GPS. Our current understanding of physics suggests that traveling forward in time might be possible, albeit at incredibly high speeds. However, traveling backward in time is a much more complex and controversial proposition. One theoretical concept that offers a glimmer of possibility is the wormhole. Imagine spacetime as a sheet of paper folded in half, with two distant points on the paper touching. A wormhole is like a tunnel connecting these 2 points, providing a shortcut through spacetime. By traversing this tunnel, one could theoretically travel vast distances across the universe, or even journey through time. However, wormholes remain purely theoretical. Their existence has not been confirmed, and even if they do exist, the technology required to create or manipulate them is far beyond our current capabilities. Some physicists believe that wormholes might be inherently unstable, collapsing before anything could travel through them. Others propose that exotic matter with negative mass energy density might be required to hold them open, a concept that is still highly speculative. The concept of time travel, particularly backward time travel, is fraught with paradoxes that challenge our understanding of causality and logic. One of the most famous is the grandfather paradox. Imagine a scenario where a time traveler journeys to the past and prevents their own grandfather from meeting their grandmother. This action would seemingly erase the time traveler's own existence. If they were never born, how could they have traveled back in time to alter their own past? Such paradoxes raise questions about the consistency and nature of time itself. One proposed resolution is the Novikov self-consistency principle, which suggests that if time travel is possible, the laws of physics would conspire to prevent paradoxes from occurring. Any action taken by a time traveler would simply become part of the pre-existing past, unable to alter it in a way that creates a contradiction. While intriguing, the Novikov principle remains a theoretical construct, and the true nature of time travel, if it is indeed possible, remains a mystery waiting to be unraveled.